So if we were to write a law, so I'm going to kind of go through the motions again here. A change, whoops. So a change of position always requires a change in time. So change in position, I could call that delta S. Now the reason why I'm going with delta S is that is sort of classical way to describe position. It'll ultimately in vectors work out to delta X, delta Y, delta Z because we have X, Y, and Z directions that something can change in. We even use R for position. Okay, so S and R are sort of classical ways to encode for position. The reason for that is we like to use P for momentum because there's some Latin word that relates to momentum. I forget why we picked that. I'm going to go with delta S. You guys use delta P. That's perfectly fine as long as you know what you're talking about in that one. And then I'll stick with a change in time is delta T because that is pretty classical. We use the little t for that. Okay, so a change of position is obviously equivalent to itself. Delta S is dependent on delta T. Okay, which implies that we need to take special care with time and treat it as an independent quantity, which makes it this fancy form of 1. If you're independent, you get to wear fancy pants. I guess that's a way to look at it. And so delta S equals itself. This is our dependent quantity. And I can multiply it by the independent quantity. Still just an identity because it's just multiplied by 1. This is an almost axiom because it's ready to encode for what the law describes, which is something always requires. And so if I continue on here, then I'll have delta S per delta T times that delta T. And so this always requires business has now been encoded for. Change of position always requires a change in time. Okay? Now the axiom has encoded for what the law describes. So what is the ratio of a change in position to change in time? Have you ever looked at a meter, like perhaps on your way to school today? Was there something in your face the whole way to school that was a delta S per delta T? What's that? That gauge in front of your face, behind the steering wheel, speedometer, something in miles per hour, kilometers per hour. It's a change of position per change in time thing. It's measuring the speed of your car that changes if you press the gas or the accelerator button or pedal. All right. So what we have here, this boils down into delta S So the trick is, what do we name this? And we call this speed or velocity if it has a direction. All right. And so this means a formula could be this right here. Delta S, a change in position, is equivalent to the same but not the same as speed times the change in time. Distance equals rate times time. That formula you did a few word problems on in algebra class. All right. This is our basic motion equation. It's the first motion equation. In fact, what I call it the first, and this sounds strange, Zeroth, that's an R, law. Now, why do I call it the first Zeroth law? Well, there was this dude named Newton, you might have heard of him, who had the first, second, and third laws of motion. He's kind of famous and important, and I'm kind of not famous and as important to physics as Newton was. So, but Newton didn't do this work as far as anyone knows. He didn't go to the backstory, but all of his work encompasses it for sure. And so I said, all right, well, this is the Zeroth law. And so the first time I wrote this, or we wrote it, me and my old grad advisor, we called it the Zeroth law until we realized, wait a minute, there's not just one of these. There's another one of these. So we said, okay, this is going to be the first Zeroth law. So Newton had 1, 2, and 3. I got to go back to 0 since I think it's foundational to his laws. All right? Now, if you were to turn to, say, probably chapter 2 in most any physics textbook, the very first thing that they'll card out is a position equation, or sometimes what they'll card out is the speed equation, which would just be, you could write V equals delta S per delta T. That's typically where a physics book starts, is with the velocity equation or speed equation. Now, they also call that the average speed. So when you go to read about this, if you haven't already, they will call this equation right here average speed. Now I got a question for you. When you look at that, why would a subtraction divided by another subtraction, how is that anything like computing an average? Isn't averaging adding up some things and dividing by the count of those same things? Yeah. Everybody and their dog knows that that's how you compute an average. So how is it that the ratio of two differences is the same sort of thing as the count, the ratio of some counts, some sums and some countings? That makes no sense, right? Okay, it will make sense next Wednesday when we sort out what an average is and how this really is an average speed. Okay? But at face value, I just want to say that just because if you haven't read it, you will. They call that average speed. And that's weird. It always bugged me when I was an undergrad. It never totally made sense of it until later, why that was an average. Okay? It worked out as an average, but it didn't make any sense to me at the time. All right. This thing right here, speed, velocity, that is a construct. Okay? We gave it a name and a symbol. We constructed new knowledge. Because guess what? It's not going to be a constant. I mean, it can be. If every change in position is the same amount relative to a change in time that's always the change in time is always a second, and the change in position is always a meter, or it's always 2 meters, well, then you are going to have a constant speed. So it's possible to have a constant speed, but it's not necessary. There's nothing about changes in position that require speed be constant. But a circle, if you remember back to the circumference and diameter, no matter what happened when we divided any circumference by its diameter, we only got one number. So the physical reality of a circle demands a constant. The physical reality of motion does not demand a constant, but it does demand a construct. And so speed could be anything, all right, as provided that there's non-zero time associated with a change in position, all right? So I'd been mentioning construct versus constant, and I wanted to emphasize that before this video. So measurable quantity number 1 is change in speed, which we use V for speed. We also use it for velocity when it's a vector, when we know the direction. Change in time, still what it is. And of course everything is identical to itself. So we can always write them as identities, all right? It is the case that a change in speed is proportional, or it's dependent on a change in time. I can't have one without the other. And so that means that I need to make a fancy form of 1 at a time, and then I write my dependent identity. I put the fancy form of 1 with it, which means I get a delta V per that. And so once again we get a new construct, and the trick is, what do we name that thing? What is the time rate of change of speed? It's a word that's almost identical to the thing that causes the change in speed in your car. That thing that you put your foot on. The accelerator. So acceleration. Acceleration is the name of this construct. And again, there's nothing about this that's required to be constant, because I could have any change in speed associated with any other change in time. So there's nothing about changing speed. If speed wasn't required to be constant, a change in speed isn't required to be constant. All right? It can be constant, like in the case of gravity. Gravity has a constant acceleration associated with it. And so our delta V equals A delta T. And this is the second zeroth law. Or what I would call sizzle. The first one was fizzle, FZL, first zeroth law. Second zeroth law, SCL. The statement of law is in English. Okay, so this is the axiom for the second zeroth law. It's another way to state the second zeroth law. And from this, you could write acceleration is delta V per delta T, which is essentially what we said over here. If you look in a physics textbook, they always start with V equals delta S per delta T and A equals delta V per delta T. They don't start with the other form. They list it, but they don't start with it. And they give the definition, but they don't give the backstory. All right? And so it's important that you construct that backstory yourself. Gives you a conceptual foothold that in the long run makes the doing of physics simpler because you are more familiar with everything that's underneath the hood, so to speak. All right? Back here, change in speed always requires a change in time. And so here's a change in speed, and here's a change in time. There's a this per that. I can sort of see the always requires mathematically in that axiom related to that law. But over here, so somebody tell me, step 1 says expand the left-hand side of this equation. How do you expand a delta anything? So it would be a difference of two instances of that variable. And so what I'm going to do is I'm going to have S minus S sub 0, which is essentially the same as an S2 minus S1 or an S4 minus S3 or an S11 minus S5, okay? It's a final value versus an initial value, and the sub 0 is referring to time equals 0. That's how we do that. Now you might see things like so other things that you might see would be S final minus S initial equals V delta T, where sub F and sub I refer to final and initial. There's multiple ways that they go at it. But if there is no subscript on a letter in physics, we mean that's the final amount for that interval. And a sub 0 or a sub any number would indicate at what time index. Okay? So those are just some of the linguistic rules of the game. So we have two equations here. One of them is the one we started with. The other one is just a rearrangement of those things. But here's what I want to point out to. Verse 2. Number 2, isolate the term representing the final value of the variable. Okay, that's easy. S equals S naught plus V delta T. Now I have 3 useful equations. How would you say that in English without using words like add and multiply and equals? What phrase would go with S? S is the final position. So the final position is equivalent to position plus, well, what is V delta T? Look up at the top. It's a change in position. Isn't this really basically the sum of the parts equals the whole? So what you end up with finally has to be what you started with plus whatever changed. Technically speaking, you could write any quantity this way. So mass. The final mass is going to be equal to the initial mass plus the change of mass. The final force is going to be equal to the initial force plus the changing force. The final speed is going to be equal to the initial speed plus change speed. The final this is going to be equal to the initial this plus the change in this. It wouldn't matter what the quantity is. You could start with final equals initial plus change in that same quantity symbolically. Everything we do in science could be written that way. But the trick is, or the important deal is, yes, I can write a change in something, but if I don't know what the structure of that change is, and I don't have a way to measure it, then I'm stuck. I've said something that's trivially true, but if I don't know how to build or measure that change, then I don't have anything except a great idea. So it's important to be able to construct that change. What are its parameters? So the parameters of a changing position are speed and time. Distance equals rate times time, right? So I've sort of said number 3, and so if you want to, you can go back and watch the video and see what happens. Number 4. So expand the left-hand side of the second zeroth law axiom. So I think, we're really just difference in letters here. And then we want to do the same thing, isolate it. And of course, that's V naught plus delta V. And once again, this change thing is encoded for by that set of parameters in a product relationship. So this product relationship business, products were really simple and sweet when it was just 2 times 2 is 4. Okay? If I have 2 sets of 2, there must be 4 things. If I have 3 sets of 3, there must be 9. Man, it was great when that's all a product involved. But now products involve multiplying things that, well, can you see speed, acceleration, or time? Can you see those things? No. You cannot see speed, acceleration, or time. You can see that something's moving, and you perceive that it has a speed, and you can even perceive that its speed is increasing, but you can't see speed. You can see objects, you can see places, you can see objects going from place to place, and this object went from that place to the other place faster than some other object did. Or you might have see that it started off slow and then it got faster. But speed isn't a substance, it isn't an object. It's a perception, and it's a perception that can be quantified, it can be measured. So if we go back to those questions, what can I see? What can I measure? So I can measure something that I can't see. Because it's built out of things, well, one of the things, position change, I can see positions. I can see objects at locations. But I can't see the time parameter that's associated with speed. And I can't see the speed change or the time change that's associated with acceleration. All right? So again, we end up listing 3 equations, actually 4 equations per thing. So there's this equation, and these 2 versions of the same thing. So there's really 4 versions of each law axiom. Guess what? One of those will be more useful in certain problem-solving situations than the other. And all they are rearrangements of one another. Oh, we forgot one. There's a 5th one. I already showed it, though. I can take this thing and go, oh, that's V equals delta S per delta T. But I didn't put it on this thing because we'd already done it on our previous watch column. So there's actually 5 versions of each law axiom. Just mathematical rearrangements. Trivial stuff for you at this point in your education. All right. Turning the page. So this first part of getting to the zeroth law theorem was just reviewing the first and second zeroth laws and mapping out their variations, building a formula sheet in one sense of the word. So now we're going to build a theorem. This might be the first time you've built a theorem. You might have seen some theorems stated in math class, especially if you took calculus, but you probably haven't built one before. So we're going to do that today. So here's these 2 law axioms. And the question that I'm going to ask in here that's not written, is there anything about the motion? These are 2 ways to describe the motion of an object. I can talk about its position change, or I can talk about its speed change. What do these 2 descriptions of motion have in common? Time. Isn't the time that it took to change position identical to the time it took to change speed? It's not like they're working on different time scales. If it wasn't moving and it moved from here to there, then it had to obtain a speed. That was a change in speed from 0 to whatever it ended up being at the new position. And the time interval between the speed change and position change was the same time interval. So it is the case, necessarily, that this change in time and that change in time are the same change in time. So it is the case that delta t equals delta t. Well, delta t over here would be delta s per v, and delta t over here would be delta v per a. Okay. So this is an axiomatic theorem, and theorems always obtain when you do this sort of maneuver where the common element of 2 other functions stand in equivalence, and then you bring in what they're equal to. Then you create what's called a theorem. And so a theorem would relate 2 or more laws. That's what's happening here. All right. Now I tell you, let t equal t and then flatten or get rid of quotients using the appropriate arithmetic. So a ds equals v dv. This is the Zeroth Laws theorem axiom. It's an axiom, it's not the law, it's a version of the law. But what would the law statement be? So think up here. What sort of law statement should or could we make to make sense of this? So how would you combine the 2 English statements that you must have on paper by now? Every change of position always requires a change of time. Every change of speed always requires a change of time. How would you combine those most simple way?
Each change of position and speed requires a change of time.
Each what?
A change of speed and position requires a change of time.
So yeah, it's so simple. It's seemingly hard. Every change of position and every change in speed require a change in time. They're never separated. from one another. Well, could I have a constant speed that results in a change in position?
Yes.
Is a constant speed a change in speed? No. Okay. So here's the thing. When I look at ADS equals VDV, there is nothing about the law statement that makes that math obvious. I would have a hard time writing ADS equals VDV if that were the law statement that I started with. Because I see change in position and I see change in speed in my law statement, but I don't see a change in time, nor do I see acceleration and speed as constant values, or average values actually is what they are in this case. So that's the weird thing about a theorem, is the English version of it, I can't call it a law. So really when it comes down to it, this is sort of wrong. This thing right here, it's not the law because it's a theorem. But the parts of the theorem, or where the theorem came from, its laws do come together in that statement. So this is a law-like statement whose axiom is a theorem built out of laws. So the pattern here is, we kind of broke our pattern. All of our prior law patterns in English had the measurable quantities specifically, and those things showed up in the math. And in this case, we created a new thing, and that shook out constructs of speed and acceleration. But then when we bring these together, the thing that they have in common, the only thing that's identical in the first and second Zeroth laws, I get this new equation, and the law that it would be if I combined its law statements doesn't really lead me to that equation. Because I can look at the other two laws. Change in speed. Okay, that's there. Change in position, that's there. But I don't have a change in time. And that's because change in time has been locked up in those critters. Because the definition of those critters is where the time is hidden, etc. So it's not as obvious. That's why it is called a theorem and not a law. It's a theorem about the laws. And it has a law-like statement, but I can't generate it from that law-like statement unless I already know some other things. Right? So, little subtle. So the Zeroth Law theorem states that acceleration times a change in position is equivalent to this speed times the change in speed. Technically, that's almost correct. The thing that's missing is that this is an average speed. Now, I told you that V is understood as average speed, even though nothing about delta per delta communicates the idea of an average. You're not summing anything, you're not dividing by a count of anything. Okay, but it is an average. And so average speed, and we're gonna build the average speed formula next week. We're gonna build it graphically. We're gonna use graphs of motion to build this formula. which we haven't done that yet. And then we're going to relate the first and second zeroth laws back to also to graphs. All right. So this formula ADS really equals 1/2 V plus V naught delta V. And of course, this works out. I can get rid of that half by multiplying a 2 on both sides. And I have V plus V naught times V minus V naught. Well, that is a difference of perfect squares. So this right here is the zeroth law theorem axiom. And this right here is your standard textbook version of the ZLT axiom, except the way that that axiom is built. And the way that that axiom is built, if they show it in your book, is it's just a mathematical, it's witchcraft. It's just mathematical sorcery. If I take time out of this equation and jam it into that one and shake it all up, then I get this out. All right? But that's not, this doesn't make any sense. In fact, I'm going to, so that we can get out at 11, I'm going to bring that up on screen.